or?
He gave those.
Okay, so very good. Okay, good.
And then, do we know what happened to Austin Jarrett's going through test? Austin Jarrett's? This is the only one that's not it. And he has a multiple choice score, so.
Would one of you be willing to give the prayer?
Yeah, I can do it.
I don't even know if he's in our class. He just-
But if I had like a laser inside, it was out of phase with the light coming on.
It's actually going to be here tomorrow because I work on Tuesdays.
So otherwise, like, normally it would be.
Welcome, everyone. Let's go ahead and get started. We'd like to begin with prayer, and so Jason is going to give us some prayer today.
Our Father in heaven, we're grateful for today, and we're grateful for the world that we have. We're grateful to be here today to learn more about biochemistry. Help us that our minds will be open, and Dr. Cruz will be able to help us learn and understand the concepts. We're very grateful for the blessings of the liberty that we have, and grateful for the Thanksgiving season that helps us to focus on gratitude. And these things we say in the name of Jesus Christ.
Amen. Thank you. So let me say a couple things. Obviously, today is the last day that the exam is available through the testing center, so please plan accordingly. I don't think it's particularly busy. I've been told that, so but do give yourself adequate time to be able to take it. If you are going, it's probably useful to take a calculator. There's one question that involves a series of calculations, and so you should have a calculator that can do log functions. I did prepare a handout relative to our special topic that we are continuing today, talking about metabolic disease. So I have posted that on Learning Suite, so please look at that. There will be questions on the exam related to our discussions last class and today. I have had some queries about the final. The final obviously will not be in the testing center. The testing center is not open. Students will not be on campus for the most part, except those who have jobs that require them to be here. It will probably occur on a single day at a single time. Now, our class is divided into several sections, and so there are 2 or 3 times, scheduled times, that are available for our class to take the exam. Those are on, I believe, Tuesday and Wednesday of the final period in the afternoon, but I haven't chosen a specific one. I'll try to do that in the next day or so and firm that up. So just be aware, I will continue to do review sessions through Zoom, and you're welcome to use those to prepare for the final. You're also welcome to schedule other times to go over material with me. So anyway, that is where we are. I will rely a fair amount on slides today. I know that's not as, perhaps as engaging as a lively discussion in the lecture hall, but that's not going to happen today. So let me bring up some slides. We're going to now discuss diabetes, and let me give you a bit of context. These are some current figures related to diabetes. You can see that over 10% of the population, the adult population in the United States, has diagnosed and undiagnosed diabetes. There are those who have it but may not know it. There are an additional large number of people who have a condition called pre-diabetes, and we'll talk a little bit about what this means. But overall, we are talking about at least a third to a half, maybe more, of the adult population. Actually, it's more than that. We have a lot of people in the U.S. who have difficulty with the disposal of blood glucose. So the issue arises, so diabetes, pre-diabetes have formal diagnostic criteria. We'll talk about those in just a second, but the implication is that these individuals are at risk for a number of complications that come with diabetes, including kidney failure, vascular damage, and sometimes loss of digits, toes, fingers, lower extremities in particular are vulnerable, blindness, cardiac disease. It's a silent, but it is a deadly disease. The problem, or one of the problems, is that the prevalence of diabetes and prediabetes has grown enormously over the last couple of decades. And it has grown in conjunction with individuals being overweight. So this seems to be a very substantial risk factor for diabetes. So hyperglycemia, or diabetes, has some historic characteristic problems, things that people become aware of. The disease itself and its effects on the heart, the kidney, the eyes, and so forth are silent, but people often are aware of things being different because historically there are these three sort of diagnostic, or not diagnostic, but are signs and symptoms of the disease. So if I can just direct your attention. So polyuria, polydipsia, and polyphagia are these three characteristic features of diabetes. So let's walk through them. Diabetes means that there is an increase in blood sugar, but an actual difficulty in getting sugar into cells. And there are two reasons for that happening. So there are two general types of diabetes. As a consequence of this inability to meet the energy needs of cells, there are signals within the organism that cause us to eat more. So we feel like we are starving to death even though we're eating adequately, 3 meals a day, maybe more. Nevertheless, individuals with diabetes tend to eat and eat because their bodies are signaling that they're not getting adequate cellular energy. This leads to an increase in osmotic particles in the circulation. All that glucose, the lactose, mannose, fructose that is in the circulation leads to an increase in osmotic pressure, drawing liquid into the bloodstream. So we tend to be volume expanded. This is accompanied, this increase in osmotic concentration, osmolality in the blood leads to our consuming lots of water. So people will drink not 1 or 2 liters in a day, they will drink 4 or 5 or 6 liters of water in a day, and not surprisingly, their urine output, the polyuria, means that they are constantly having to use the bathroom. That is to say that frequently they become aware of this because they're getting up 3, 4, 5 times in the night and have substantial urine output. So these are classic features of diabetes. A single blood test, a fasting blood test, if you are confident that the person is fasting, may be sufficient to diagnose diabetes, but often it is not. Often one requires a more rigorous test, and this is the oral glucose tolerance test, OGTT. People are brought into the clinic fasting. They are given a drink called glucola. It is nauseatingly sweet, and they are expected to drink this within a 10-minute period, and then they monitor their glucose levels before they take in the glucola, and then hourly for 3 hours after this. This is a formal clinical test to officially diagnose diabetes. As mentioned, there are 2 broad categories of diabetes. The more uncommon, the rarer form is type 1 diabetes. This has to do with the destruction of pancreatic beta cells and the loss of insulin production and secretion in an individual. In the absence of insulin, the body cannot place the GLUT4 transporter in the peripheral tissues, in the membranes of peripheral tissue cells. Consequently, glucose is not readily disposed of. And this is called type 1 diabetes. It used to be called insulin dependent, and it really is insulin dependent, but it turns out that some type 2 diabetes also requires insulin. We'll talk about that. Type 2 diabetes is initially the body is able to produce insulin. In fact, it produces very high levels of insulin, but the insulin seems to be ineffective in getting glucose uptake into cells, or at least it has lost its efficiency. So there is this insulin resistance, that is, for a given level, concentration of insulin in the blood, there is less glucose uptake in a type 2 diabetic than in a normal individual. All right. We'll come back and talk about hemoglobin A1C in a minute. So diagnosing diabetes does involve measuring glucose. And so a fasting glucose, if one is confident that the person really has undergone an overnight fast, if you have a level above 125 milligrams per deciliter, that is diagnostic for diabetes. However, if somebody has had a snack, has had a drink of juice, or had some other kind of caloric intake prior to the test, those glucose levels will be artificially high, and so they may be above 125 for reasons other than, well, because they've taken in food. Normally, our blood glucose levels, as we mentioned, are between 70 up to about 100 and 108. But so generally, if we have a blood glucose below 100 on a fasting blood, we are normal. But if you have levels between 100 and 125, there is a suggestion that you are not able to utilize glucose efficiently. So this pre-diabetic state, they sometimes will refer to this as glucose intolerant. They will sometimes talk about this as impaired glucose uptake, impaired glucose utilization. All of these are referring to this situation where you're not disposing of glucose adequately. So as part of an oral glucose tolerance test, once we take in the glucose, we at 1 hour typically, or 2 hours, our blood sugar levels are below 140 milligrams per deciliter. In a pre-diabetic, this ranges up to from 140 up to 200. Above 200 or 200 and above is diagnostic for diabetes. So let's just look at this slide for a minute. In the stippled area, we have our normal individuals. This probably doesn't show you adequately the range of values, but remember, if you are below 140, you are okay. So you can see that blood glucose in most individuals peaks at around 60 minutes. However, it could be a little bit later depending on the individual. In mild diabetes, and I would characterize this probably as type 2 diabetes, or maybe even pre-diabetes. Well, this is actually mild diabetes because the levels do reach 200. They do exceed 200 at 60 minutes. But what you see is that the individual, the blood sugar levels go high, but then it takes a long time to get rid of the circulating glucose. And this would be then typical of a type 2 diabetic. They produce insulin. The insulin results in an inadequate number of GLUT4 transporters inserted into peripheral cell membranes. Consequently, it takes longer to dispose of a glucose load. But you can see, as plotted here, that they do, with time, get the glucose into the cells. This requires a higher level of insulin to accomplish even this than is found in a normal individual with normal glucose control. A severe diabetic is typically a type 1 diabetic. You can see that their levels are high to begin with, go higher after eating, and stay elevated for a very long time. So it is very hard for them to dispose of a glucose load. Right. I want to talk a little bit about hemoglobin A1C. And let me go to this slide. So with high blood sugar levels, there is a process called glycation, protein glycation, that takes place spontaneously within the blood or within the vascular compartment. So these are proteins that are present in the circulation, but they can also be proteins on the epithelial layer that surrounds or represents the interior layer of a blood vessel. The blood glucose, the glucose or other sugars spend some time in their open and elongated form. It's not a high fraction for glucose, it's higher for fructose. But what happens is the aldehyde or the ketone species will interact with primary amines, so lysines or N-termini of these proteins. They will form an imine, which is this condensation reaction. And it is in equilibrium. If you have higher levels of glucose, a larger fraction of the sugar will be attached to a protein. Now, this is a reversible process to begin with. But then there is another spontaneous rearrangement that occurs that produces an irreversibly attached sugar coupled to the protein. And these accumulate. As long as the protein is in the circulation or presented to the blood, it will continue to add these sugar groups. And this begins now to impair the function of these proteins. And in fact, these glycation products, as they become more extensively glycated, actually form aggregates. And these aggregates will activate receptors called RAGE. So these are receptors for advanced glycation end products, RAGE. So what is the significance of this? Well, the issue is that when you have an individual in the clinic and you're trying to evaluate how well controlled their glucose levels are, you have them at the moment. And usually, in anticipation for going to the doctor, they will be very careful about their diet. They'll be very careful about their insulin utilization if they're a type 1 diabetic. And consequently, their results will typically be better than what happens broadly over a prolonged period of time. It turns out that by measuring the glycated protein, and this is done by measuring hemoglobin A1C, this is a glycation product that coupled to hemoglobin, that you're able to get an integrated, this is the idea, integrated snapshot of how well their glucose levels have been controlled for the past 30 to 60 days. And this has to do with the turnover rate of red blood cells. But nevertheless, if they have about 6% or less of the glycated protein hemoglobin A1C, then that is considered to be normal. You can see that a pre-diabetic, so still able to dispose of glucose, but not necessarily taking good care of themselves because they don't know that they have the disease necessarily. They're going to have somewhat higher levels. And then diabetics, under good control, probably have levels that are around 6.5% on up. In a poorly controlled individual, I have seen hemoglobin A1C levels that approach 20 to 25%. So these individuals are at significant risk for all of the complications that occur with diabetes. All right. Okay, type 1 diabetes is an autoimmune disease. There are a few other circumstances whereby you might generate type 1 diabetes, but it is an autoimmune disease, and the body produces autoantibodies that attack and destroy the pancreatic beta cells, and with their destruction, one loses the ability to produce and release insulin. These people absolutely need insulin provided or they cannot survive. And so this happens by way of intramuscular injection. The problem is you could take insulin, but it would be orally, but it would be rapidly degraded in the small intestine, and it would have no effect. So these individuals then require constant injection of insulin, sometimes multiple times throughout the day, to be able to remain in glucose control. Now, one might ask, well, What causes the autoimmune process? And this is a question that is unanswered for any autoimmune disease. Some speculate, and this is speculation, that if you have increased levels of something called oxidative stress, where the body produces and allows to circulate increased levels of reactive oxygen species, such as superoxide, hydrogen peroxide, hydroxyl radicals, that these can injure, can damage proteins and produce oxidized species. And some propose that these oxidized species are sufficiently different from the normal unmodified protein that they can, in some cases, generate antibodies against themselves. They now look foreign to the organism and are targeted for removal. The problem then is that if there's enough cross-reactivity with these antibodies produced against these oxidized species, be they proteins or maybe even lipids, that these antibodies also bind to and damage normal protein, because there's enough homology structurally that they can. This slide shows the results of studies looking at one autoantibody type, and it's looking at type 1 diabetics. And what you see is that those who have type 1 diabetes, that at least in this study, 2/3 to 3/4 of these individuals had measurable levels of this particular autoantibody, that targets the pancreatic beta cells and destroys them. You'll also notice that there are a few controls that also have this autoantibody, which suggests that in a period of months, maybe years, that they too will suffer from type 1 diabetes. So it is an autoimmune disease. Type 2 diabetes is really, again, poorly understood. It's well understood in terms of its signs, symptoms, complications, and so forth, but in terms of its causes, it is not well understood. They have, they have studied this for decades. They've understood that this disease is marked by, to begin with, high levels of insulin, but a diminished response to the insulin, or insulin resistance, in these individuals. They have explored the insulin receptor. They've looked at the glucose transporter. They've looked at its numbers, its composition, its response, and the elements of the glycolysis pathway and other pathways involved in glucose management, and have found nothing that explains this enormous number of individuals who have type 2 diabetes. There is a strong familial association with type 2 diabetes. This is not the case with type 1. It would be rare to have two individuals in the same family that had type 1 diabetes. So there's not a strong genetic predisposition to type 1 diabetes, but there is a strong genetic predisposition to type 2. As mentioned, 90% of individuals in this country, at least, who have type 2 diabetes are overweight. And many of these individuals, or many others, are physically inactive. And these are really substantial risk factors for the development of type 2 diabetes. But why they are is, again, not well understood. The process that brings GLUT4 to the cell membrane allows it to be placed in the membrane with insulin's stimulation. Somehow it doesn't work quite the way that it should. This disease, type 2 diabetes, tends to be progressive. That is to say that to begin with, the pancreas beta cells produce more insulin. They will try to compensate for this insulin resistance. They will generate higher insulin levels for the same glucose load, but even so, it still takes longer for the cells, the tissues, to take up the glucose than happens in a normal individual. As this process persists, the pancreatic beta cells lose their ability to sustain these high levels of insulin. And so there is something that is sometimes referred to as fatigue, but it simply means that the production is lost, or at least is reduced. This particular type of diabetes is treated by diet. So it's type 1 to some degree. One has to manage one's carbohydrate intake very carefully. Type 1 is treated with insulin injections, but type 2 often can be managed with weight loss or with exercise. Remember, we talked about the AMP kinase being able to lead to GLUT4, the GLUT4 transporter being put into cells independent of insulin. So that is that has a very favorable effect on this. Metformin is the drug of choice for type 2 diabetes. It inhibits the liver's ability to release glucose, so either from glycogen breakdown or from gluconeogenesis. As mentioned, with time, the insulin levels cannot be sustained, and that is sort of what is shown here. You can see clock time on the x-axis, and with meals, you can see that in a normal individual, the stippled area, insulin production is very substantial, but in individuals who have had or continue to have type 2 diabetes, there is an inability to achieve as high levels of insulin as a normal individual. That's also shown in this slide. So for a given glucose concentration shown here on the x-axis, you can see that this NIDDM, non-insulin dependent diabetes mellitus, those individuals have type 2 diabetes. They're just not able to produce the levels of insulin that a normal individual can. And consequently, type 2 diabetes, as their disease persists for a decade or more, end up often having to take insulin supplements by injection to be able to meet their needs. Okay. Again, let me just point out that people have studied this disease for decades, and the actual direct cause of this initial insulin resistance, its inability to provide adequate uptake of glucose, is not understood. Now, there are those, including some on this campus, who propose that the problem is that if you eat carbohydrates, you will get diabetes. If you eat a lot of sugar, you're going to get diabetes. The clinical studies do not support that. I have reviewed many reviews of this, And while there are a few studies that suggest that high glucose intake or high carbohydrate intake may impair glucose utilization, probably 90–95% of studies show no effect of carbohydrate intake or no causative effect of high carbohydrate intake on long-term glucose utilization or short-term glucose utilization. Now, if you have prediabetes or you have type 2 diabetes, then carbohydrate intake does make it worse. But there is no evidence at this point that high carbohydrate intake causes diabetes. Okay, let's talk very briefly the sugar levels. Okay, the sugar levels that that stay high, go high, stay high, cause modifications of proteins. These glycation products, especially the advanced glycation products, cause problems. They lead to damage of blood vessels. Those are the proteins being exposed directly to these high levels of glucose. This leads to problems in the kidney, in the small vessels in our peripheral tissues, our fingers and toes. They affect the blood vessels in the eye. And when those vessels become damaged, the eyes undergo a process called angiogenesis, where there are additional blood vessels grown in the eye, and this can cause blindness. You lose the ability to see because you now have these new blood vessels blocking the visual pathway. The endothelial layer is this inner layer of blood vessels that gets damaged by these glycation products. It leads to other problems. It activates other systems that tend to make things worse. And so in the end, people suffer substantially from reduced circulation to their lower extremities, their toes, their fingers. They often experience damage to their kidney, which can be complete chronic renal failure. And we talked about the eyes. The heart also can be damaged. In terms of acute or immediate effects of high blood sugar, there really are not any serious ones. We talked about drinking more, urinating more, eating more. But it is true that if you are a type 1 diabetic and you do not get insulin, then the body switches to using fats as a source of energy. This generates lots of what are termed ketone bodies. These can drop the blood pH to a point that is incompatible with life. So, all right. Are there questions? Is there anybody out there? We're going to spend a couple minutes introducing the processes that generate ATP in the mitochondrium. So we've talked about high energy molecules, NADH, FADH2, produced as part of the citric acid cycle, produced by the pyruvate dehydrogenase complex. These electrons, this energy, this electrochemical energy, is moved through a set of complexes that are termed the electron transport chain. And this leads to the pumping of protons across the membrane, and as those protons re-enter, they actually are used to generate ATP. And this is the process that we're going to talk about for the next couple classes. So let's get introduced to the mitochondrion. The mitochondrion is this very interesting organism. I mean, not organism, organelle within the cell. It is the energetic hub of any cell. It is by far and away the place where most of the energy handling takes place. It is organized, it has two separate membranes. It has an outer membrane, which is fairly, and you can see here, it's not well demonstrated, but oops. You can see that there is an outer membrane, and then there is an inner membrane. So the outer membrane is kind of a shell that is around all of the contents. This particular outer membrane has openings in it. It has what are termed porin channels. These allow molecules up to molecular weights of 5,000 to enter and exit through that membrane easily. The inner membrane, though, is folded. It has these deep indentations in it. So that is what is being shown here. So let's say this one right here, what we have is then a fold, and it is a very deep fold. Sometimes they go almost entirely across the mitochondrion itself. This inner membrane is very impermeable. Almost nothing can enter the matrix, the center of the mitochondria, unless it has a special transport system to get it across this inner membrane. The citric acid cycle is in the matrix. It's within the inner membrane. The electron transport chain is actually embedded in the inner membrane. So it's actually membrane bound or membrane installed. It's insinuated in the membrane itself. And the ATP synthase proteins are also associated with the inner membrane and extend into the matrix. So this is the general organization of the mitochondrion. This is an actual photomicrograph. Again, you can see these deep invaginations. The advantage of having these folds is that it gives you much more surface area than the outer membrane. And as mentioned, all of the machinery for all of the complexes of the electron transport chain and the protein complexes involved with ATP synthesis are in the inner membrane. So you can have many, many, many more copies of these available if you have more surface area on the inner membrane. All right. I think I will stop here. We'll come back and we'll talk about the elements that handle the electrons, the proteins that make up these complexes of the electron transport chain. The proteins don't actually handle electrons. There are other factors, organic compounds, inorganic compounds, that are embedded in these proteins or attached to these proteins that actually allow for the electrons to move through these complexes, undergoing a series of oxidations. That energy is harnessed to pump protons from the inner space, the space between the outer and inner membrane, the intermembrane space, to the mitochondrial matrix. We'll talk about this more next time. So let me ditch this here. All right. So I was going to share with you an experience that I had. This is now many years ago when I was still living in Massachusetts. I served as a time as the Young Men's President in our local ward. And on one occasion, I attended a youth conference with the youth of our state. And as happens at most youth conferences, the there was a lot of fun. We did some service projects, but the concluding event was a testimony meeting held on the Sunday of youth conference. And as part of this testimony meeting, a young man from my ward got up to bear his testimony. This young man had lost his brother. His brother had died in a very sad and terrible way recently. And I know, and this young man was quite close to his brother, both in age and they were quite close friends and family members. And so the loss of his brother had been very, very hard on him. So as he got up to bear his testimony, he got underway, and he hadn't spoken for very long before he broke down. He just simply lost it and began crying at the pulpit. After this had gone on for just a brief time, a young woman from another ward got up and went up to the podium and put her arms around this young man from my ward and just held him as he cried. She just stayed there at his side and comforted him as best she could. With time, he regained his composure and he completed his testimony, and the two of them sat down. It turns out that this young woman had recently lost her mother. Her mother had died during childbirth of her younger brother. And this had been a devastating loss to her family because there were many young people still at home in this family. But I thought about this experience often. It was a little bit out of, it didn't follow protocol for her to get up and go to the podium. I didn't see the adults get up and go to the podium and support this young man. But she did. She was willing to sort of think outside and act outside the box to bless and comfort this young man. I have wished that I had that same level of compassion and maybe courage to stand up and to move to somebody's side and to lift and sustain them in their hour of need. I think it's something that we can all consider as we live our lives, that there are going to be those around us who are hurting, who are in need of a friend, a helping hand, a lift, and I hope that we can be the ones to move to their sides and embrace them as if we were the Savior. Anyway, something to think about. Thank you very much. We will meet. I will have another class tomorrow at this time on Zoom, and I will be having my office hours. if you want to join, starting once I get back to my office. So anyway, good luck to you all if you haven't taken the exams.